In this video, we're going to be talking about Newton's method, and Newton's method is definitely one of the most tedious sections in Calculus 1. It's definitely not something difficult, and it's not something that's hard to wrap your head around. It's really just a tedious section that's very time consuming, and it really just tests your ability to use a calculator. Um, Most times you won't see it on a test. If you do, you'll be given one at most to do. Simply because of how time consuming of a process it is. And in this video, I'm really going to go over the basics of it. I'm not going to do really any examples. I'm going to do one basic one, and I'm going to just set you up for other ones you might see in the future, simply because it's very easy to implement. It's just it takes a long time to solve these guys. So Newton's method, though, it does have its advantages in that it helps us find the zeros of a function, or at least approximate them. If we were given a linear function, like y equals 2x plus 1, finding the zeros is no problem. If I had y equals x squared plus 2x plus 7, okay, we could still find the zeros. If I had y equals x cubed plus 4x squared plus 2x plus 11, well, we could use some methods from pre-calculus, such as the rational zeros test, but that method is very time consuming, almost as time consuming as Newton's method. So you can see really as we up the degrees and so on and so forth, then finding the zeros becomes a harder process. So Newton's method helps us. So Newton's method helps us basically just find the zeros or approximate them at higher degree functions. So Newton's method helps us approx zeros of higher degree functions. And that's really the basic idea of it. It can also help you approximate basically where two curves are intersecting, and basically where they're hitting the x-axis, where basically where x is um, or sorry, where y is equal to 0. So let me finish this real quick. Functions. So it's really basically, finding the zeros for all these guys. We set y equal to 0, and for linear functions it's easy. Get x by itself. For here, maybe factoring or quadratic formula. Here, if we set y equals 0, maybe rational zeros test. But as we up the degree, we also up the difficulty. So Newton's method can help us take care of these guys and onward and onward. And that's really the main purpose of it. And without going too much into the theory of how it's implemented, I really think it's beneficial if we just do a couple of examples and I really introduce the formula. So the formula here is x sub n plus 1 is equal to x sub n minus f of x sub n over f prime x sub n. So really keep this formula in the back of your mind. It's definitely one that's worth remembering. It's really the main one for Newton's method, actually. If you know this, you can definitely implement Newton's method no problem. Uh, but another obstacle in learning Newton's method is how we implement this guy. So I'm just going to do an example really quick. Let's say we're given f of x equals, and I'll write example over here. Example. Let's say we're given f of x is equal to 2x cubed minus 3x squared plus 2. And we're given that x sub 1 is equal to negative 1. Negative 1. If it's not written like this also, you'll see that, instead of f of x, it'll just be set equal to 0. Either way, the context of the problem, it'll say use Newton's method. So you could either have it as f of x or 0. It depends on really the instructor or the textbook. So you can see here that I'm given x sub 1, and that'll usually be the case. You're usually going to be given a starting value. So our job is we want to find x sub 3. So what is x sub 3? Well, you can see here that if we look at this this definition up here, basically the next term relies on the previous term. So for example, if I wanted x2, then I'd have to use x1 in this definition, and so on and so forth. You can see that's the case because if I just let n equal 1, well, I would say x sub 1 plus 1, that's x sub 2, is equal to x sub 1 minus f of x sub 1 or f prime x sub 1. If I wanted x sub 3, then I'd let n equal 2, so 2 plus 3, or sorry, 2 plus 1, that's 3. But number n is still equal to 2, so I'd have f x2 minus f of x2 over f prime x2. So really, the term that you want next, the next term you want, this one, is going to rely on what came before it. So if we want to get to x3, we really need to find x2 first. And in order to find x2, we need to use x1. But before I do any of that, let's just start by taking the derivative of this guy, because I can see that in my formula, I'm going to need the derivative. So, this is just basic power rule. This is basically just going to be 6x squared minus 6x. Okay, so far so good. So now I have the two things I need, and all I have to do is really just find x sub 2. So let's do that. So if I wanted to find x sub 2, then remember that x sub 2 will be using the previous term. So the one you want right now, will use what came before. So if I want x2, then here I'm going to have x1. So x1 minus f of x1 over f prime x1. And you could see here, if I wanted x sub 3, then I'd use x2 minus f of x2 and so on and so forth. If I wanted x4, then I'd use x3 in my formula. If I wanted x5, then I'd use x4 in my formula, and so on. So let's approximate, or at least just calculate what x2 is. Well, remember what x1 even was. x1 was given to us. x1 was given as negative 1. So I'm going to have x2 equals negative 1 minus f of negative 1 over f prime negative 1. And now all I have to do is just plug this in. So I'm going to have negative 1 minus, well, f of negative 1, my f function is up here. So I'm going to have 2 times negative 1 cubed minus 3 times negative 1 squared plus 2 over 6 times negative 1 squared minus 6 times negative 1. And I did this calculator work ahead of time. I didn't really want to just sit here while you guys listen to me press buttons on my calculator. The result of this guy, this turns out to be negative 0.75. This is my x2. This is x2. Okay, so now let's find x3. So to find x3, remember, to get the one you want to use what came before. So I'm not going to use x1, I'm going to be using x2. So x3 equals x2 minus f of x2 over f prime x2. Okay, so now all we have to do is really just plug in, because remember what x2 is. x2 is negative 0.75. So this is going to become negative 0.75 minus f of negative 0.75 over f prime negative 0.75. Okay, and this one I did the work ahead of time. But just to recap really quick, 10-second recap, is basically all I did was I plugged x sub 2 into this equation, negative 0.75, f of negative 0.75, f prime negative 0.75. To get these values, well, to get f of negative 0.75, I would just plug that in, negative 0.5 in over here, to this one I'm pointing at right here. If I wanted f prime of negative 0.75, well, then I plug it in over here, and that's it. So doing the calculator work, obviously, you're not going to be able to do this fast on a test or anything like that, but you're going to get something about negative 0.6825. and it's negative 0.6825. And that's my x sub 3 value. That's my x sub 3 value. There we go. So down here, very neatly, I'll write x sub 3 equals negative 0.6825. And that's rounded to 4 decimal places. It goes on after that. This is a rounded result to 4 decimal places. So that's really the essence of Newton's method. And obviously you're watching this and might get frustrated because the homework might look a little different. But what you have to know is that the principle is the same. That if it tells you to find x sub 3 or something, you're good. This example will get you through those types of problems. But if it basically asks you to approximate the zeros of a function, basically what you're going to do is you're going to go on and on and on with this until your decimals match up to some extent. So for example, just for example, let's say that x sub 4 equaled, I don't know, like negative 0.5834, and then x sub 5 equaled negative 0.5899, or sorry, to be too big, 5812. X6 equals negative 0.58, basically 1, 1, and then x sub 7 equaled negative 0.5811. Really what those problems are asking, where it just keeps asking you to, like approximate the zeros and everything like that, or just basically just use Newton's method to find what's called the real root or just the root, then you would just keep doing what I was doing here. You'd get some x values, some x sub 4, x sub 5, and you just keep going on and on and on and on, doing the same exact process I just did until you basically get 2 consecutive decimals that match up. Once they match up to, in this case, 4 decimal places, and it's always going to be specified as well. Like it'll say approximate the root to, I don't know, like 6 decimal places or 4 decimal places. So if it's asking for approximation to 4 decimal places, then you want these the 4 decimal places of 2 consecutive terms to be the same. So so here, like, these first 4 weren't the same, so I didn't pick that. But here they were. Once they start becoming the same, then it's going to be very, very obvious that that's the answer. If it asks you to 6 decimal places, then you would need the first, I don't know, like 6 to be the same, like that, or something like that. So pretty easy process. Really not much to it. It's just a matter of plug and chug. Again, don't quote me on these x sub 4, x sub 5, x sub 6, x sub 7 values. I really just pulled them out of the back of my head. In no ways are these accurate for this function. At least I don't think so. One more thing is that not all of the time it'll ask you to find it. Not all the time, basically, it'll ask you to find it and give you a value. Like let's say here, let's say I had a function like this, -1, and then over here, I had like -1 or something. And it basically wanted these 2 values right here. You would basically want to find those. Then in this case, you'd have to do it twice. You would say x sub 1, and then you can pick your x sub 1. You can pick it. You would have to pick some value near, or some value near this, or near this. So, here I would say, okay, -1, and here I'd say 1. But the closer you are to wherever this is, the less steps it's going to take to get that. And then, you find x sub 2 using the formula, f of x1 over f prime x1, and same thing down here, and so on and so forth. That's if you're given the graph and no starting x value. No starting x value. So you would pick the points. You would just pick some point near it that you know. And here, I'd pick 1 and -1 because those are close. Even better would be like, maybe 1.3 or something and -1.3. Those would be even better. One last thing before I end this video is that sometimes it'll also ask you to basically it'll ask you to do the same thing, find the roots, or basically it's like it'll give you 2 graphs and it'll say like find the real root, and it'll just give you a graph like this or something. What it's asking for there is it's asking for this point right here. And again, like let's say this is like no, let's say I have like my 2 over here. Then, I'd pick 2 and that would be my starting value. And um, I'd basically just use both of these equations, put together. Like if this was like, I don't know, let's say I had, for an actual example, let's just say I had something like this. Let's say I had like that, and then I had like this or something. Let's say I had x minus cosine x equals 0. That's this graph right up here. Then, I'd be looking for my x1 would be, I don't know, let's say 2. That's some value near where they intersect. And then I'd find x2 the normal way. I'd do all of this stuff I did up here. Same process. Again, that's why I'm not doing these, because I would just be doing this formula in front of you guys for about like 30, 40 minutes straight, and that's really not that entertaining unless you're into that, but it's really just a straightforward process. So again, to recap, if they give you an x sub 1 value, do exactly as I've done here. They'll give you an x sub 1 value. Usually that'll be the case. And if they ask you to like find x sub 3 or x sub 4, do exactly what I did here. Do exactly what I did to find x sub 3. If they don't give you an x, or sorry, if they don't give you like a stopping point, like if they just say find the roots and this wasn't here, that guy wasn't there, then you would just keep going until however many decimal places they want line up. Usually it's like 6, or it'll probably be like 4 on test or something, because that's shorter to find. So yeah, you do that if they didn't give you a stopping point. If they also, if they just give you a graph and they want the roots, then you pick your x sub 1. You would pick some values near where they intersect the x-axis. So let's say -1 and 1, because that's near these points where they intersect the axis. And if they just gave you, 2 curves intersecting each other, and they give you the equation, then you would basically just find out, a good point that's near where they intersect and do the same exact thing you've always done. The process is the same, just the contexts are what's different. So again, rewatch this video a couple times in order to get the instructions of how to do these certain types of problems. The only other type of problem I could think of is where they didn't give you a graph and they would just give you x minus cosine x or something like that. And that's when you would just have to graph it on your own and really approximate where they intersect. It's just really one extra step. You're just graphing and then you're doing Newton's method. So rewind this video if you need to, go over how I implemented Newton's method, and then go over the instructions of how to do the other types of problems you might see in your homework or on an exam or something. But that's really all I have to say about Newton's method, and as always, if you want me to cover any other math topics, feel free to message me. I'm open to anything from pre-algebra to calculus 2. So as always, thanks for watching.